Alright, this is number 76 from Chapter 4. It reads, a 28 kilogram block is connected to an empty 1.35 kilogram bucket by a cord running over a frictionless pulley. The coefficient of static friction between the table and the block is 0.45, and the coefficient of kinetic friction between the table and the block is 0.32. Sand is gradually added to the bucket until the system just begins to move. Calculate the mass of sand added to the bucket and calculate the acceleration of the system. Okay, so a couple different things. Number one, it's going to incorporate two types of friction, and then the other part about this is the fact that you've got the cord which connects the two, and you need to remember that the tension in the string throughout the whole string is exactly the same. And the reason that helps us is because it allows us to neglect it for much of the problem. Okay, so I'm going to draw a couple pictures here. Here's the 28 kilogram object. It's going to have an F of G and an F of N, and friction will be acting this way. Okay, and then we've got the bucket. Okay, which is 1.35 kilograms. That would have an F of G this way, and this is where it matters because there's this string that connects it right here. So there's a tension force up, and then there's a tension force this way. But if the tension forces are the same, then I can basically just forget about them. Okay, so the one thing to understand, if we know the mass, then we know the F of G. 28 times 9.8 gives us 274. F of N would have to be equal because this box right here isn't burrowing through the table or flying up into the air. Therefore, this is 274. And in order to get it going, you have to overcome the coefficient of static friction. So in that case, friction would be equal to the mu of static friction, 0.45, times the normal force, 274. Okay? And if you do that, you get 123 newtons. Okay? Now here's what I know. If I'm going to need to get this object moving or get the system moving, these two forces are balanced already. It's not accelerating up and down. That means that F of G has to be equal to or greater than the force that it's fighting against, which is friction. So F of G in this case must be 123. Now what this allows me to do is it allows me to solve for the mass of the sand that has to be added, because I already know that this is 1.35. I can tell you 1.35 times 9.8 is not 123. Okay, so if I want to find the mass, the total mass, F of G divided by 9.8, or in this case 123 divided by 9.8, you end up with 12.6, but don't forget you also have to subtract off the 1.35 kilograms. Okay, so for letter A, the amount of sand that you would need would be the difference, and I'm going to round to 11.3 kilograms of sand added. Okay, so that's the first part. Okay, part B says, okay, well now that it's moving, what is its acceleration? Okay, now reminder that the force of friction is going to change when it starts moving because mu of K is less than mu of S. Okay, so I'm going to solve for my new friction value now that it's moving using 0.32. And still the same normal force because remember this is the box, it's actually on the table. So that's 274. So I get a force of friction equal to 87.7 newtons. Well, if that's the case, if this right here is now 87.7, 123 and 87.7 do not cancel. So we have an unbalanced force. Okay, so the sum of the forces is now the F of G of the hanging mass, this one, minus the force of friction, that one. Okay, so we end up with 123 minus 87.7, so that would give us an unbalanced force of 35.3 newtons. And now if I want to solve for the acceleration of the system, okay, it would have to be, let me see here, mass times acceleration. We've got 35.3, and now be careful with the total mass. You can't just use the 11.3 kilograms because it's also in the bucket, right? So we said that the total mass was 12.6 kilograms plus the 28 kilograms, so that's a 40.6 times A. So A, or the acceleration, ends up being 0.87 meters per second squared. And that's number 76.